So today we're happy to have Waseem Bakr from MIT. Waseem got his degree with Marcus Greiner at Harvard, graduated from Harvard in 2011. And he was the graduate student, among the graduate students, but I think the primary graduate student setting up the quantum microscope that Marcus has gained a lot of interest in. And in a paper from 2010, I believe, won the Newcomb Prize for the AAAS, of which Waseem was the first author, and it was also, I think in 2010, one of the top scientific breakthroughs according to Science magazine. Waseem won the 2012 DAMOP Thesis Prize Award and has since moved to MIT, a long transition down the street. Actually going back, because you were an undergraduate at MIT, right? So it hasn't gone very far away from Cambridge. It hasn't made it across the river even.
Yes.
But anyway, he's now a postdoc working in the group of Martins Weierlein. And so today we're going to hear about condensed matter physics with ultra-cold atoms.
Thank you, Steve. And thank you all for being here on holiday. So what I'd like to do in this talk is to tell you about some experiments from what I've done during my PhD and during my postdoc with Martin, trying to use cold atom systems to study condensed matter physics. So I'll give examples on multi-insulators, for example, and I'll also tell you about some experiments we're doing in the direction of studying topological matter with cold atom systems. So first let me introduce the systems we use, which I'm sure many of you are familiar with. So those are very dilute gases, which you have in a vacuum chamber, completely isolated. And the typical spacing between the particles is on the order of a micron or so. And we cool them using a combination of laser cooling techniques and evaporative cooling down to nanokelvin or even picokelvin temperatures. And at those temperatures, the de Broglie wavelength of the particles becomes very large, and degeneracy effects kick in. So, of course, what started this field was the realization of Bose-Einstein condensation back in 1995, and that was in a weakly interacting gas. But very quickly, the field. So there you start with quantum optics experiments and so on. But very quickly, the field moved on to studying strongly correlated physics using two main techniques, both of which you'll see later in this talk. So the first technique is the technique of optical lattices, where you can use periodic patterns of light to reduce the kinetic energy of the atoms so that the interaction effects are stronger. So this was, for example, very important for seeing the multi-insulator, the superfluid to multi-insulator transition with cold atoms. And the other main technique is the Feshbach resonance, which was particularly useful for fermions, where you can now tune the scattering length between the atoms. And this was useful, for example, in studying the crossover from Bose-Einstein condensation of tightly bound molecules to Bartini-Cooper-Schreiber superfluidity of Cooper pairs. So we have these two very useful tools. And with that, the community started looking at what sort of strongly correlated materials you can look at in real condensed matter systems. So things like the cuprates, like topological phases, quantum magnets. So all of these are very complicated materials, and to study them, what typically is done is you try to abstract out to get the essential physics of what's going on in these materials with a simple model, like the Fermi-Hubbard model, for example, in the case of the cuprates. And now there's this first step, the modeling step, where things might go wrong. But there's a second step where you now have a many-body system within this model which you would like to solve, get things like properties of the ground state or dynamical properties. And again, something could go wrong there because you have to do some approximation techniques when you're trying to do the theory. So basically where cold atoms kick in is in the second stage. They can realize exactly the models that people in condensed matter use in a very clean way and can help us get solutions to these models in a sense. So why use ultra-cold atoms? The main thing is that you have a lot of control over these systems. So for example, if you consider atoms in an optical lattice, those are the analog of electrons in a crystal potential. And unlike the crystal, you can tune a lot of the properties of the atoms. For example, you could tune the tunneling rate between different lattice sites simply by changing the laser intensity, which creates the lattice potential. So you can do all of this in real time, dynamically, and you can also realize very clean systems with no impurities. Of course, if you want to add impurities by hand, you can do that. And these systems are understood from first principles, so you can sort of start with these simple systems, which you can write very nice Hamiltonians with, which you might know how to solve, check that you get the results you expect, and build complexity upwards from there. But most important for the next few slides I'll be showing you is the large spacing between the atoms in these systems. So as I said, it's on the order of a micron, so that's 4 orders of magnitude larger than in a solid. So what this means is now you can use, first the dynamics are very slow. It's on the order of milliseconds, so it's easily measurable in the lab. But more importantly, you can use optical techniques to image and manipulate the atoms in these systems. And that's what the first part of this talk is going to be about, this optical technique to look at, which we developed at Harvard, called quantum gas microscopy, which we use to look at individual atoms in an optical lattice and study the many-body physics that happens there. And so this work we did with bosons. Now at MIT we're trying to do the same with fermions. So in the second part of the talk, I'd like to switch to fermionic systems and tell you about.
Has anybody succeeded with a fermion microscope?
So there's something like 10 groups around the world now working building.
Okay. But
yeah,
I haven't seen any publications.
There haven't been any publications yet. It's
but there's no deal breaker. It's going to happen, right?
No, it should happen. There's I mean, the same techniques should work exactly for fermions. Yeah. So in the second part, I'll tell you about some work we're trying to do to push towards realizing topological phases with cold atoms. So one key ingredient, which was actually developed at the JQI in Ian Spielman's group, spin orbit coupling with bosonic gases. We've taken the same techniques and applied them to fermionic gases, where we hope more interesting effects will occur. And I'll also tell you about related work with studying basically something like bond states that you could study with the interesting bond states you would get with these systems. We can study their analogs, Andreev bond states, within an S-wave superfluid. And we found some very huge discrepancies with mean field theory in these experiments. Okay, but first I'll start with quantum gas microscopy. So the idea there is what we wanted to do was to develop basically the analog of techniques used in condensed matter, like scanning electron microscopy or scanning tunneling microscopy, where you can look at individual atoms and try to manipulate them. So the result of this work was what we call quantum gas microscopy, and this is a schematic of what our apparatus looks like. Inside the vacuum chamber, we have this hemispheric lens, and we put a gas of rubidium atoms very close to the surface. So the surface helps us in a couple of ways. It helps us prepare a two-dimensional gas, which is really important for these experiments because once you have high resolution, you can only image a single layer at a time. So it helps us in the preparation of a two-dimensional gas. And then also by putting the gas very close to a surface, you can actually get an enhancement in the resolution of your system in the same sense you would get, for example, with solid immersion microscopy or oil immersion microscopy. So the enhancement is by the index of refraction of the glass you use here. So outside the vacuum chamber, we have a high resolution objective. So the combined numerical aperture of this system is on the order of 0.8 to 0.9. And that gives us a resolution for our wavelengths of half a micron, which is sufficient to now resolve the individual atoms within the lattice sites. So I won't bore you with the technical details of what we had to solve to get there, but I'll just give you a typical sort of sequence we use, an experimental sequence we use to get to the physics. So we start out with rubidium condensate prepared using the traditional techniques, so just evaporative cooling in a three-dimensional gas in a magnetic trap. And so now we've got this cold gas, and we move it to the surface. And there we create a single two-dimensional pancake. And now what we have is a two-dimensional Bose gas that is weakly interacting. And what we'd like to do now is to bring it into a strongly interacting regime. So what we do is we add an optical lattice potential within the plane. And the way we create our lattices, I'll just mention it here because it's sort of not the traditional way optical lattices are made. What we actually use is now our microscope in reverse to project a pattern of light that can be arbitrary onto the atoms. So we have a mask here that is made lithographically, which we eliminate with a laser beam. And that creates a pattern, and this pattern gets demagnified and projected onto the atoms. So they now live in this new potential. And in principle, the pattern you use could be arbitrary. So the experiments we've done are with square lattices, but you could use a triangular lattice if you're interested in studying frustration, for example, or a Kagome lattice, or your favorite condensed matter lattice. Okay, so now in the presence of the lattice, we started out with a ground state, this Bose-Einstein condensate. We ramp up the lattice adiabatically. And what we end up is now a many-body state, a strongly correlated state, where the atoms are still now in the ground state. And we'd like to extract some information about this ground state. So the next thing we do is we quickly increase, after preparing this ground state, we quickly increase the depth of the lattice 100-fold by reducing the tuning of the laser beams that are used to create this potential. And now the atoms are suddenly pinned in the lattice, they don't move around. And we eliminate them with resonant light, near resonant light, in a molasses configuration. So they scatter a lot of light, and we collect quite a good fraction of it, about 40% or so, on a CCD. So those are the sorts of images we get. Each one of these green dots here is a single atom. So when we're trying to do physics with the system, what we typically do is we just freeze the density distribution in this many-body state and image it. Now, for fun here, I just wanted to show you what happens if we reduce the depth of the pinning potential along one of the directions. Now, remember, before, if this was a superfluid state, before the imaging step, each one of these atoms was in a quantum mechanical superposition over all the lattice sites. And only during the imaging, they get projected onto their position. So basically, we've taken a snapshot of the many-body state. But during the imaging process, that you're scattering photons, so the atoms heat up. And so if your pinning lattice is not deep enough, they can start to thermally hop around. And that's what you'll see in this movie. So those atoms are now thermally hopping between different lattice sites along the vertical direction where the potential is shallower. But in traditional sort of physics mode, we just freeze the atoms and take a picture. And the way these experiments work is you destroy the sample in the process, and you prepare a new one in half a minute or so. So you extract all the information you can, like density correlations, density, and so on from a single shot, and then you prepare a new system. Okay, so this is now a picture of a much larger, denser, and colder cloud. And you can see that we can prepare systems with thousands of atoms, and we can basically extract information about the position of the atoms in individual lattice sites. Here we have an underlying square lattice in this system. I'd like to mention here one caveat which has been circumvented in later experiments, but was there in the images I'll be showing you in this talk. And that is that what we actually image is not the number of atoms on the lattice site, but actually the number, the parity of the atom number on the lattice site. And the reason for that is that if you have a lot of atoms on the lattice site, and you eliminate them with resonant light, what you get immediately is a lot of light-assisted collisions that take out the atoms pairwise. So they form molecules that are very hot, and they get ejected from the trap. And you're only left behind with an atom if you initially had an odd number. So what you get is a parity imaging, but it turns out for most of the experiments, this was actually a very nice feature to have, as you'll see shortly. So in later experiments now in our group, what we've done is we've circumvented this problem by putting the atoms in a different plane. And now you don't have this parity imaging, or at least it becomes like modular 4 imaging. Okay, so the natural physics to study here is the physics. We have bosons in the lattice, so the natural physics to study is the physics of the Bose-Hubbard Hamiltonian. So what you have,
There's a stick there. If you want to use it for the moment.
Okay, so we have two terms, a tunneling term and interaction term. Okay, so the atoms can tunnel between neighboring sites with a matrix element J, and whenever they're on the same site, they interact with a repulsive interaction U. And the neat thing about optical lattice experiments is that you can vary the ratio between those two terms over several orders of magnitude simply by changing the depth of the lattice, which exponentially suppresses the tunneling. And now, depending on which of the two terms dominates, you get different ground states. So if we start in a regime where the lattice is really shallow, then the tunneling is dominant, and you can ignore the interactions. And at that point, the state of the system is each atom is completely delocalized over the lattice. If you look at any individual lattice site, you have a little mini condensate with a well-defined phase. But the conjugate variable fluctuates a lot. So if you have a lot of mini condensates with well-defined phase and you turn off the lattice suddenly, what you get is all these condensates expand, overlap with each other, and you get a matter wave interference pattern. And now, if you increase the depth of your lattice so that the interactions become dominant, and you can forget about the tunneling, then what happens is that the number of fluctuations are suppressed. You don't like to have a lot of fluctuations, which could lead to a lot of atoms on a given lattice site, because that would cost a lot of interaction energy. So what you end up with, rather, is preferring to put a fixed atom number on each site. And so that's a Mott insulator now. And since the atom number is fixed, the phase is not defined anymore. So if you now release the atoms from the lattice, there is no matter wave interference anymore. And these sort of matter wave interference pictures are how this transition was first observed back in 2002 in Munich. And what we set out to do with our microscope is now try to look at the reciprocal picture in real space. Basically see this change from a lot of fluctuations in the superfluid to having a Mott insulator. So this is what we saw when we looked at a small patch of the cloud. So this is increasing lattice depth from left to right. There's a lot of number of fluctuations in the beginning, and then those get suppressed as you go towards a Mott insulating state. We can verify this is a superfluid by looking at the matter wave interference pattern that vanishes. And if we do a correlation measurement on the defects we see there, which are now, because of the parity imaging, actually could be doublons or could be holes. If we do a correlation measurement, we can verify that far in the Mott insulator, those are no longer quantum fluctuations. So around here, you would get a lot of quantum fluctuations. But then far in the Mott insulator, all you have is thermal fluctuations. Due to the temperature of the sample, initially, if you have a cloud that's not at zero temperature, then you would get some defects. And also due to maybe non-adiabatic ramping of the lattice. So those could introduce those thermal defects. And as a matter of fact, it turns out to be the most sensitive way to do thermometry in these systems, to just count the defects directly.
Where should I think of the transition as? I mean, it's a finite system, I understand that. Is it between 12 and 16 somehow? Because the first three pictures look pretty much the same to the naked eye.
Yeah, there isn't much of a sharp transition.
It's all crossover.
Yeah.
Has anybody done, I mean, these are, how many bosons do you have? How many particles do you have there? 10,000?
Typically between, no, it's more like 1,000.
1,000. So I can do a warm algorithm. I can exactly simulate the system. Right? So has anybody done that for your finite system to reproduce exactly these figures?
Yeah. This Lode Pollitt.
Lode has done.
Yeah, has done basically exactly the simulation to figure out
including the background optical trap potential. Everything.
Yeah, you have a smooth background,
right,
non-uniform.
Yeah.
But one algorithm can include that. I mean,
yeah.
And does it reproduce exactly this sort of crossover?
Yeah, I don't have the graphs here, but you can reproduce the data.
The square root of n, of course, is relevant.
It's large because it's 1,000.
Well, the square root of 1,000 is only 330,
Right.
and that's short.
Okay, so this is what we see when we look at the local patch of this gas, but we can also now zoom out with the microscope and look at what's happening more globally. And there, because of we need a harmonic confinement in addition to our lattice potential to keep the atoms from sort of drifting outside our laser beams, because of that potential, we can get some very interesting structure that appears in the cloud. So to understand that, you can start in the multi-insulator regime and try to imagine what happens when you add more and more atoms to your sample. So in the beginning, you prefer to put one atom per lattice site because of the strong interactions. And you add more atoms, and they go towards the edge of the sample. And eventually, it makes more sense, rather than climbing up this harmonic potential, to start putting atoms in the center of the sample. So this is the start of the formation of a second shell in the multi-insulator with 2 atoms per site. And so if you keep adding more atoms, you'd expect to get something like 3 shells, 4 shells. And with the parity imaging, which is where now this parity imaging is really nice, you would get actually basically a shell with 2 atoms would vanish, and then you'd only see the shells with 3 atoms and 1 atom. So you get a nice contrast there. And we've done this experiment, this code experiment now in the lab, so these are actual experimental pictures now. And you can see this formation of the shell structure in the multi-insulator as we increase the number of atoms. So we start with 1 atom per site, then second shell with 2 atoms, then 3 atoms, and over here, 4 atoms per site. So we've studied other things about this system, like density-density correlations across the quantum phase transition. We've looked at things like dynamics. For example, when you quench from a multi-insulator to a superfluid or the other way around, there's some interesting dynamics to look at. We've actually used this system too as a way to study magnetism, but I don't have time to go into that.
Do you understand the reason there's a point at the bottom rather than circular symmetry on the lattice?
Okay, so this is basically, if it's an ideal harmonic trap, they would be perfect circles. In this case, the beams which we are using to produce this potential are slightly irregular. So there could be some deviation from circular symmetry. So this is a way to figure out sort of the equal energy contours in your potential. Okay, so in the second part of this talk, I'd like to switch now completely from these bosonic systems to fermionic systems. And so what we're interested in pushing towards in the long term is to study topological phases of matter. So I'll just give a brief overview of why I think this field is really exciting and how it's been evolving in condensed matter. So there's this Landau symmetry breaking scheme that was and still is very important for classifying different states of matter. For example, you can distinguish crystal from a liquid by symmetry breaking. You can distinguish, for example, a superconductor because it breaks gauge symmetry. But then people realized with the discovery of the quantum Hall states that this wasn't the only scheme of classifying different states. You could have different quantum Hall states which do not break any different symmetries, but rather they're still different phases because you could define topological invariants associated with the different states which you do not go smoothly between. So those are sort of like for example, a donut is the same as a coffee mug topologically because they both have holes in them. And then more recently, this field has received a lot of attention because of so with quantum Hall states, you have to apply this large magnetic field to get to these states. But more recently, people discovered things like topological insulators, where now you don't have to apply a very large field to study the same physics. So you preserve time reversal symmetry. And the thing that now takes the role of the magnetic field is a large spin-orbit coupling that is intrinsic to the sample. So this is a single particle term in the Hamiltonian you add. But it can actually lead to very interesting physics because in the presence of spin-orbit coupling, even if you had, for example, contact interactions, the spin-orbit coupling can lead to a modification of the interactions to have longer range P-wave interactions, for example, which could lead in fermionic systems to unconventional pairing. And there's been a lot of interest, for example, with realizing superfluids with this pairing because they might exhibit Majorana fermions, exotic particles that have, for example, non-abelian exchange properties. So what got us thinking about doing this was, as I mentioned, the experiments from Ian Spielman's group at NIST, where they realized basically the spin-orbit coupling term in this Hamiltonian. And the idea they had was, Okay, so we take a cloud of atoms, in their case bosons, in our case fermions, it doesn't matter, and you shine laser beams from two opposite directions on them. And you pick the difference in frequencies between those laser beams so that you can do a Raman transition between two different hyperfine states, which we use as our pseudospins. So we label this one spin up, this one spin down, and now this Raman transition provides a coupling between those two. And in the process, the atoms absorb one photon from one of the beams, they stimulatedly emit into the other beam, and they get a momentum kick due to this absorption and emission of the photon. So now what has happened is that the atoms flip it, spin, and they get some momentum transfer. So we've coupled the spin and momentum degrees of freedom. Now in condensed matter, the sort of Hamiltonian you would write for electrons is this one. So here you have the kinetic energy for the electrons, and then you have a spin that interacts with the B field. And this B field can be decomposed into three parts: the Dresselhaus part, the Rashba part, and the Zeeman part. The Zeeman part is basically momentum independent. And then you have two other parts, which are symmetric and anti-symmetric in momentum, that are the Rashba and the Dresselhaus contributions. So with the cold atom system, we realized basically this Hamiltonian with a spin-orbit coupling whose strength we can have control over from the geometry of the beams. And in addition, we have Zeeman fields. So this is now an equal part Rashba-Dresselhaus Hamiltonian. If you use laser beams from more directions, you can actually engineer, for example, pure Rashba or pure Dresselhaus Hamiltonians. But it turns out this sort of spin-orbit coupling already leads to some very interesting physics in the presence of interactions. And then, in addition, there's Zeeman fields, which are both transverse and longitudinal to the spin-orbit coupling. And again, we have control over those terms. In the case of the longitudinal field, with the tuning from the two-photon resonance, and the Rabi coupling strength gives us control over the transverse field. So all the terms in the Hamiltonian are controllable, and it's a single particle Hamiltonian, so it's easy to diagonalize. If we switch off for a second those fields, and we just have the spin-orbit coupling, then what we get is two parabolas that are displaced relative to each other in momentum. So they're displaced relative to each other in momentum. This is for spin up and for spin down. And now when you turn back, for example, the transverse field, what this does is it opens a spin-orbit gap between those two bands. And now, so the system is decomposed into two helicity bands. If I follow one of the bands, the bottom band, as I change the momentum from negative to positive, the spin flips from up to some sort of superposition of up and down, encoded in the color, to being fully down.
Is this a one-dimensional system or a two-dimensional system?
This is a one-dimensional system. And now I can increase the strength of the Rabi coupling, and that will increase the spin-orbit gap strength. Okay, so this is the single particle physics. And now the interesting stuff, of course, we can study the single particle physics by going to a non-interacting system because we have control over the interactions through a Feshbach resonance, for example. But we can also now think about adding the interactions back in. And what happens is, if we take two fermions that are at the same momentum, because our fermions are really cold, they only interact through S-wave interactions. So here they would have the same spin composition at the same momentum. And because of the Pauli exclusion principle, you cannot now scatter. If I try to increase the relative momentum between the particles, now their spin composition is changing. For example, if I go really far away here, it's completely up and completely down. And so now they can start scattering. So effectively what's engineered is we started out with an S-wave interaction. You add the spin-orbit coupling in, and now you have an interaction that depends on momentum. In other words, it's a higher partial wave interaction, which was demonstrated with bosons, for example, in Ian's group. And the dominant contribution in the case of the fermions would be the P-wave contribution. So that could lead to some interesting effects close to a Feshbach resonance as proposed by Professor Dosarma's in some of his papers. All right, so now we did this experiment with the fermions. What you see here is a picture of a cold cloud of lithium, a degenerate cloud of lithium. And this is a time of flight picture. So we basically let the atoms expand, and you take a picture of the Fermi sea, prepared here in the upspin. And now what we did next is we turn on the spin-orbit coupling. And what we changed is basically the longitudinal field. So we control the position of the avoided level crossing. And what that does now is, in the presence of this coupling, you basically take some of the atoms in this upspin and put them in the downspin and give them some momentum. And you can now sweep the position of the avoided level crossing, and you take out a slice from this upspin and put it in the downspin.
Can we see that again?
Sure. Okay. You have any questions? Okay, so the next thing we set out to do was to basically verify that we had engineered this sort of system. So we'd like to measure the dispersion, but this is not just an E versus K dispersion. It's a dispersion that also has color in it. And basically, this is what we're doing here is the analog of in condensed matter spin arbis, which they use to basically measure how the spin changes inside your band. And the idea here is that we can start with the atoms. So it's the opposite of arbis, what we're doing here. We're doing injection spectroscopy.
So this is more like STM than that.
Yeah.
STS. It's more like scanning tunneling spectroscopy. You're looking directly at the band structure.
Yeah. So we start out with atoms in two reservoir states, one of two reservoir states, and we start out with a spin orbit coupled system empty, no atoms in there, and now we inject atoms from the reservoir states into the spin orbit coupled set of states by sending in an RF photon, a radio frequency photon of the correct energy. So we know the energy of the photon, and this would lead to a transition at a well-defined momentum. We can measure that momentum by releasing the atoms and doing a time-of-flight experiment to measure that momentum. And then we can also do spin-selective imaging to figure out whether the atoms, the composition of the spin of the system. So we can basically reconstruct this band structure together with its color. And so we've done this for this simple system, and we get what you expect. So this is in the absence of a spin-orbit gap, and as we increase the spin-orbit gap strength, as we increase the Rabi coupling strength, you open up a larger spin-orbit gap. And we've done this in more interesting sort of systems where we can, for example, engineer a lattice with a band structure that is spin-orbit coupled. And so this technique turns out to be really nice there. Okay, so the next thing, the next natural thing to do with the system is now to add the interactions. It turns out here we're using lithium. We're adding the interactions back in. We can always add the interactions back in, but the interactions are only interesting if you can prepare an S-wave superfluid of lithium in the presence of the spin-orbit coupling and a transverse field. Now, it turns out with lithium, because it's such a light atom, the intrinsic spin-orbit coupling of the electron there is very small. So you get a lot of scattering, which makes the spin-orbit coupling term of the Hamiltonian incompatible with having a superfluid gap. But if you go to heavier atoms, so now we're going to try to do this with potassium and possibly heavier atoms, there you would expect possibly to reach a regime where you can be in both, have a spin-orbit coupling plus a Feshbach resonance and a transverse field, which might lead to some topological superfluidity. But as a sort of, so the interesting thing there with the topological superfluids is not really the superfluids, but the defects in the superfluids. So if you create, for example, a vortex in a superfluid or a soliton in a superfluid, then the bond states within these defects have some really interesting properties. So to take us in that direction, what we thought about was can we already, with the lithium gas we have, create some defects in there and study the properties of the bond states in these defects? And in particular, so if you have a superfluid and you create like a vortex in it, what you end up having is an array of bond states trapped in the superfluid. So actually what we create is an excitation with a soliton, not a vortex. And I'll tell you in a second what a soliton is. But before that, since I haven't said anything about S-wave superfluidity in these gases, let me just remind you how that works. So the magic tool here is what I mentioned earlier, the Fashbach resonance. And what this is basically a way to bring two colliding free atoms of different spin states into resonance with a molecular state. And these two states have different magnetic moments. So by tuning a magnetic field, we can bring them into resonance. And at that point, the scattering between the atoms diverges. So this side of the resonance is called the Bose-Einstein condensation side of the resonance, because there you would get tightly bound molecules, and now you can just think of them as point bosons, which would condense. And on the other side, you have Cooper pairs of fermions, which would lead to BCS-type superfluidity. And by tuning the magnetic field, we can smoothly cross over. Actually, it was shown for the first time with cold atoms that you can cross over between Bose-Einstein condensates to BCS-type superfluids. And what's really neat about these superfluids is that if you go to the unitary regime, where the interactions are strongest, the critical temperature for superfluidity turns out to be about 16%. We've measured it recently, done a precision measurement of this critical temperature. It's 16% of the Fermi temperature. So if you scale sort of the densities of the gas we have to densities you have in a condensed matter system, then this would already be a high temperature superfluid. And you can verify the superfluidity, for example, by stirring the gas. So those were experiments done in our group by stirring a gas of superfluid fermions with a laser beam. And as you cross over from BEC to BCS, you see that throughout the crossover, you actually get vortices in your sample. So you can verify the superfluid. So now we've got these beautiful high temperature superfluids. And we'd like to introduce some defects in them. And the defects we use are solitons. So a soliton is basically a sort of a solitary wave that moves around in a nonlinear medium and maintains its shape. And it can maintain its shape due to a balance between the nonlinearity in the system canceling the dispersion. So here are examples of solitons that can occur in nature. So here there's a shallow water channel, and this thing here might be a soliton. Actually, that was the first context in which people thought they gave solitons their name, actually, in this context. And these clouds here might also be solitons. Okay, so now in a superfluid, you again have a nonlinear medium. For example, you can take a Bose-Einstein condensate, and that's described by the Gross-Petyaevsky equation with a nonlinear interaction term. And you can now imagine trying to engineer its phase profile, as was done in experiments, for example, by Bill Phillips and Klaus Senstock's group about 12 years ago now, 13 years ago. And so you get a jump in the phase in this superfluid. And corresponding to this jump in the phase, there's also a jump. If you take the wave function and try to engineer it, it would look, the order parameter would look something like this. So if you now take the square of the order parameter, which is your density in the gas, it would have a notch in it. And this notch is what we call, this notch in the density and step in the phase profile is what's called the soliton. The size of this notch is on the order of, in a Bose-Einstein condensate, on the order of the healing length. And this soliton can now move around in the system. And it's sort of a topological excitation, not quite, it's not like a vortex. You have to make it one-dimensional for it to be stable. And it turns out it has many decay mechanisms. For example, at finite temperature, it can decay through the emission of phonons, and actually counterintuitively, what happens is as it moves, it starts to speed up. So it's actually, in a sense, a negative mass particle. And this was studied, as I mentioned, in Bose-Einstein condensates. So this is what's called a dark soliton, and it occurs for attractive interactions. For repulsive interactions, you get a density enhancement, and people call that a bright soliton. So so again, just to set the terminology, this would be a black soliton because it goes to 0 at the notch. And this would happen if your phase step is exactly pi. And at that point, the soliton is actually stationary. If you try to now imprint a phase different from pi, then the soliton starts to move, and this density dip goes down. Okay, so now what might be interesting about doing this with fermionic superfluids different from Bose-Einstein condensates? Well, the main difference is that now you can actually have bound states that live inside these solitons. So here now what I'm showing is not the wave function like in a BEC, but the superfluid gap. And this superfluid gap crosses 0 at some point. And now in a fermionic superfluid, you only have pairing at the Fermi surface, and inside you have a normal gas. So if you take the order parameter to 0, you can have some normal fermions living inside your soliton, and outside you have a superfluid. So what you get in a sense is some sort of superfluid, normal superfluid junction. And this normal gas lives in Andreev bond states far on the BCS side. So all this picture works far on the BCS side of the crossover.
I guess I'm a little lost on the dimensionality here. Should I be thinking of a two-dimensional system or a three-dimensional
Okay, so
system?
the experiment is done in a three-dimensional cloud that is very anisotropic. The aspect ratio is about 15. And we've actually varied the aspect ratio. I'll show the different aspect ratios. Now, in the sense that this is not really one-dimensional in the sense that the chemical potential is much larger than the vibrational spacing, about a factor of 25 or so. But it seems to behave more or less like what we'd expect from a one-dimensional soliton. So basically, for example, if you go to, so the soliton in our case is actually a plane, and there's a two-dimensional fermionic gas living in there. And I think if you make it more three-dimensional, as was the case in, for example, Bill Phillips' experiments with bosons, they had a sort of a lower aspect ratio. The soliton becomes more unstable because now you have a membrane.
And then you would have thought it would break up.
And it can break up into vortices.
Okay, so I should think of this as primarily one-dimensional, but of some cross-section.
We prefer to think of it as one-dimensional, but possibly one of the decay mechanisms is for the soliton to decay into vortices.
Thanks.
Okay, so now the neat thing compared to condensed matter with our solitons is that in this atomic gas, it's really clean. So they're not pinned to an impurity. So they can actually move around in the system. And as a matter of fact, since we have the gas in a trap, they can actually now oscillate inside this trap, inside the cloud. And this oscillation of the soliton inside the cloud can give us information about the bond states living inside the soliton, because now you would expect, as you sort of fill up Andreev bond states or other types of states inside the soliton, what you would expect is that the period of the oscillation of the soliton would increase. And there was this prediction by the group in Trento, Stringari and others, and Pidevsky. And what they predicted was, they studied exactly this problem I've been describing. And what they predicted was that as you go from the regime of BEC to BCS, this is this interaction parameter 1 over KFA, KF being the Fermi momentum and A the scattering length. So here 0 would be the strongest interactions, so where the scattering length diverges. 1 would be, or this direction would be the BEC limit, and this direction would be the BCS limit. And now what they tried to calculate was the ratio of the soliton period normalized by the oscillation period for a single particle in the trap. So this is some sort of like, they're trying to measure an effective mass for this soliton in terms of the bare mass. And what they predicted was that you would get an enhancement of the soliton period as you go from BEC to BCS. And so here it starts out at about this ratio of the soliton period to trapping period at about square root of 2. And actually the square root of 2 was measured, for example, in Klaus-Sandstock's group, experimentally. And they predicted it would go up to maybe around 2 or so at 1 over kfa of negative 0.5. So this was done with a 3-dimensional mean field equation. So basically Bogoliubov de Jean here. Okay, so we thought, square root of 2 to 2, that sounds like something maybe we can experimentally see. So we followed basically the steps of Bill Phillips and others, where we take a laser beam, cover up half of the laser beam with a razor blade. So you get a very sharp step in the light intensity. And now you shine this light on the cloud. And so you get a stark shift on part of the cloud, not on the other. So you accumulate some phase difference between the two. And we try to imprint some phase on the order of pi. But we can change that by the pulse duration. And so now what happens is you create this phase step, you create a soliton, and in addition you create some sound wave because you have to take some density out of the notch, and that gets kicked out very quickly at the speed of sound, basically in the medium. But the soliton, it remains behind. So as I mentioned, those solitons, their size is typically, on the BSE side, that's the healing length. At unitarity, it would be the interparticle spacing. All these numbers are on the order of a micron or so. So they'd be really hard for us to see if we look at the cloud in situ. But what we can do is we can actually give a little bit of the time of flight, and those scales blow up a little bit, so now you can actually resolve them in the pictures. So this little density notch here is the soliton, essentially. And one thing I have to mention here is that as you start to fill up the density in this soliton as you go towards the BCS side, you wouldn't expect to see a soliton anymore because the density becomes uniform, although there's still a phase step. So what we do for these experiments is we do the experiment and then very quickly ramp to the BEC side so that we can empty out this notch and look at the soliton. So here's what we see versus time. And you can see an oscillation of the soliton back and forth in the track. And the first shocking thing to us was how long these solitons live. It's on the order of like seconds. And so basically this is given only by the lifetime of the superfluid in our vacuum chamber due to background gas collisions. So if I sum up along one of the directions here, you can see the oscillation clearly. Okay, so first thing we set out to do was to verify this prediction of going from BEC to BCS and seeing the period get enhanced. And we do indeed see the qualitative behavior predicted. So what's plotted here, these different graphs are for different magnetic fields. The Feshbach resonance in lithium is at 832 Gauss. So this is on the BEC side of the resonance, and we're going towards unitarity. And you can see very clearly that the period gets enhanced. But so the qualitative trend is correct, but in terms of being quantitative, it's actually absolutely off. So this is where the mean field sits at unitarity, for example, and the data is about, I don't know, in terms of mass, this would be about a factor of 100 off.
I thought you said that Klaus-Sandstock got the number square root of 2.
They got the square root of 2.
Okay.
So this is not far enough on the BEC side.
I see, okay.
Yeah, so
So
we can
he
only
was more on that side.
Yeah, he was doing it with the Bose gas, where the interactions are very weak.
So there is no disagreement in the data. It's just that you are much closer to the
Yeah.
unitarity point.
So we cannot push further on the BEC side because the gases become unstable to three-body collisions. So we can only go as far as this on the BEC side. But they did this Bogoliubov de Jean theory across the crossover, and their prediction at unitarity is, in terms of mass, the effective mass is 3 times the bare mass, and we see something more like about 150 or so. And this is done, you were asking earlier about the aspect ratios, so this is done for increasingly one-dimensional traps, and we believe we've sort of converged on some sort of one-dimensional limit here. So, far on the BCS side, we expect the Bogoliubov de Jean theory to work properly. Unfortunately, we can't push that far. We can only go a little bit on the BCS side, because there the temperature starts to go down, and our cloud is not cold enough to remain superfluid. So what might be happening? We went back to these Clausch-Sandstock experiments, and he had done them in Bose-Einstein condensates, but one neat thing he did in one of his papers was to put a different spin state inside the soliton. So he put some different hyperfine state, and he saw that there the period got dramatically enhanced relative to not having that different spin state. So we asked ourselves, is something like that happening in our system? So now, of course, we do have two spin states because we need the Cooper pairing, but we've worked very hard in making a very balanced gas, so we don't have any extra spins. So the first thing you might think about is maybe these are some thermal quasi-particles, some non-condensed atoms that can live inside the soliton. So we started to vary the thermal fraction by varying the temperature of the cloud. And you can see, basically, for the very cold clouds, we get this nice oscillation. We start to heat up the gas. As I mentioned earlier, now you have this anti-damping behavior where the soliton can start to accelerate because basically it wants to decay into phonons, and in the process it gets lighter, so it starts to go further and further in its oscillation, and we do see that effect. Eventually the gas is so hot it becomes full of thermal fluctuations, and these sort of thermal solitons would now collide with our soliton and kill it. So the lifetime of the oscillation, the lifetime over which we can detect the soliton goes down. This is shown here. But what was important to see was that the period is constant. So this is not a thermal effect. So now the next thing to consider is quantum fluctuations in the system to go beyond the mean field. And there hasn't been any work doing basically this system beyond mean field. I don't know if you can do Bogoliubov-Dejean beyond mean field. But people have done that with Bose gases and included the fluctuations. Basically go first order beyond mean field to the Bogoliubov equations. And the theory predicts basically that the quantum fluctuations actually like to live inside the soliton. So this is basically the density profile of the cloud, and the non-condensed fraction likes to live right at the soliton. So it seems far on the BEC side, what's likely happening in our systems is that, in the fermionic systems, is that you get pair excitations that are not condensed anymore. And these pair excitations like to live inside the soliton and probably contribute to the mass enhancement. And far on the BCS side, you get the Andreev bond states. And probably at resonance, it's a combination of the two that are leading to this enhancement of the mass. But the pair excitations are not included at all in Bogoliubov-Dejean theory. So that could be one reason why we have this discrepancy. But obviously, doing any sort of calculation there at unitarity is very hard. So the message here is basically these solitons are a really nice sort of tool that brings out the quantum fluctuations effects in these strongly interacting gases. Typically, if you measure things like equation of state of a gas, do some precision measurements, you might find some corrections on the order of a few 10% due to the quantum fluctuations. But here we're measuring effects that are orders of magnitude larger due to the quantum fluctuations. Okay, so with that, I hope I've given you a flavor of what sort of physics you can study with these systems. And what we would love to do now is to push with heavier atoms to have topological superfluids where we create these sorts of defects. And there, instead of having Andreev bond states, you would get defects like Majorana fermions. And I think that would be a really exciting direction to go in. So I just wanted to thank the students who worked on these experiments, both in Marcus's group and Martin's group, and thank you all for your attention. I'm happy to answer questions.